Hello, everyone, and welcome to another class of ATMO 620. I hope you're all doing well and you're ready to talk about thermodynamics again. Last couple of lectures, we started introducing some of the basics. We talked about ideal gas, the ideal gas law. We talked about, some very basic principles of gases, some kinetic theory. Then last time we talked about the first principle of thermodynamics. Of course, we wouldn't call it first principle of thermodynamics if there wasn't a second principle of thermodynamics, which is what we're going to talk about today. There's also a third principle of thermodynamics, FYI, although we're not going to talk about it because it's not entirely relevant to clouds. It basically says that you can never reach 0 Kelvin degrees, the absolute zero. And it does get cold on Earth. I lived in Massachusetts, and trust me, does it get cold on Earth? But it never gets minus 273 degrees Celsius cold. And so we're not going to worry about the third principle of thermodynamics in this class. But we are going to worry about the second principle of thermodynamics, which is today's topic. Now, You've probably seen this already in some of your classes, but it's always good, as we said, to refresh your memory on some of the important things. Plus, not only is the second principle of thermodynamics very important and has profound consequences on so many things in physics and in your life as well, but the main character of the second principle of thermodynamics is a state function called entropy that you're going to use one way or another, in one form or another. You're going to use in your atmospheric science life to compute stuff, to derive temperatures and so forth. And so because entropy plays an important role, even though you will not be concerned with increases in entropy and the death of the universe and whatnot, you will be interested in entropy for the rest of your life. And so welcome to the introduction of entropy if you haven't seen it before, or a refresher of what entropy is. So why don't we get started? Okay, so the first thing that we need to know about entropy is that entropy is a state function. And the reason why we introduce it is precisely because we like state functions. Now, you remember probably from last time we said we derived a bunch of functions, things like internal energy. We talked about enthalpy as well. These functions are known as state functions. And the good thing about state functions, and I cannot stress this enough, is that they only depend on the state of the gas. They don't depend on the history of the gas. And so we like them because it doesn't matter how the gas or whatever fluid you're considering got to be where it is. We don't care about the history of the parcel, the history of the cloud. All we care about is the state of the cloud right now. Because the history of the cloud, the history of the parcel that is generating the cloud, maybe you have no way of knowing that. Like, who knows where moisture is coming from? Who knows where nitrogen has been before being part of this parcel, blah, 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 blah. But if you have state variables, then you don't need to worry about such things. And state variables enjoy a whole lot of nice and interesting properties. One of which being that they can be integrated perfectly, as we said last time. I hope you remember when we talked about heat and work, we said, well, usually, if you remember, we denoted heat like this and work like this. Heat and work normally are not state functions. And so we use this delta just to say these are infinitesimal increments, but they don't necessarily correspond to what we call exact differential. Exact differential. Okay. Exact differential means that there is a function to which this infinitesimal quantity is a differential. Okay. But state functions do enjoy this property, and it makes things a lot easier. So the first thing to derive entropy, or to write down entropy in some nice form, is to imagine that we have a certain parcel. The parcel is in the state A, for example. Okay, so we're in some kind of a graph that represents the state of the gas. We are at point A, and we go from point A to point B. Assume that B is close enough to A, and let's assume that the change that we're imposing on the parcel is very, very small, and we're doing it in quasi-steady conditions, okay? And in these quasi-steady conditions, the change can always be taken back, okay? So you go from A to B, but you can always go from B to A because the small is just so small, and you made it so gently that you can always walk back. There are sometimes changes from where you cannot go back. An example related to thermodynamics is that if you cool down a parcel, if you make it cold enough, then the parcel will eventually condense. Okay, the water vapor will condense, and we'll see that in a couple of lectures. And that's okay. Condensation is fine. We're happy with condensation, but eventually enough condensation can happen and collisions can help, yada, yada, yada. And you can generate large droplets of water that, because of gravity, fall down of the air parcel. Now, this change, because of gravity, is not reversible. Okay, so thank you very much, gravity. Now we have an irreversible change, and you can't walk back. Once the cloud has rained out, you can't rein it back in, if you will. Okay, but certain transformations are or can be approximated or thought of as quasi-steady. Not quasi-steady, as reversible, because you make them so small. An example: suppose you have a piston and you have a gas in the piston. You could compress the piston a little bit, and if you do it very slowly, just a tiny little bit, then just as you compress the piston, you can expand it by the same amount in a long time, and so you return to your initial state. Did you really return to your initial state? Well, to be completely honest, no, you didn't. Because, even if you're super careful, the truth is that some heat was dispersed as you did so. There is some friction between the piston and the walls of the cylinder where you put your gas. Let's imagine that you have. God, my drawing skills are bad. I just meant to do a cylinder like this. All right, so this is the cylinder. Let's assume this is a cylinder, please. And this is the piston, right? And the gas is inside here, okay? So there's always going to be some friction as the piston moves along the walls. The friction, what does friction do? Well, friction creates heat, essentially. And this heat is energy that is then dissipated through air, if there's air around here, or through, some solid material if the cylinder is part of something else, okay? And so no change is ever reversible, which sounds like a very deep statement, but some changes are more reversible than others. Okay, let's put it like that. Okay. And so let's assume that we're going from A to B, and we're doing so very gently, and we can always go back from B to A. Okay? And then we go back to our good friend enthalpy, okay? And we analyze how enthalpy changes in going from A to B. Now remember that enthalpy, we said it was a state function, and it had a very similar functional form to internal energy. Internal energy was something like U equals mCV, where this is the specific heat capacity at constant volume times T, okay, or, delta U is that. The reason why I say I choose the delta is that if you consider the absolute value, okay, so U and the delta here, then there may be some kind of a constant that you have to measure, and we don't know how much this constant is, and so it's just easier to talk about changes. At the end of the day, if we're being honest, at the end of the day, what truly matters when we consider these things is not the absolute value of something, of an energy, of enthalpy and such, but it's changes of these variables. Okay, and so so the universe is still going to exist modulo some constant factor that we're going to add, and so let's just consider changes. Okay, so here we're just considering infinitesimal changes. So instead of having a delta like this, we're just use the d for differential. It's legitimate to do it like this because this is a state function. So this equals, this is going to be constant because we're assuming no changes in the gas, Cp dt. But H, if you remember, was also defined in terms of heat and in terms of volume and pressure. And this was the relationship to heat. Infinitesimal changes in enthalpy were infinitesimal changes in heat plus V times dP. So we can divide all these terms by temperature, okay? And we have mCp dt over T. So we're just dividing this by temperature, divide this by temperature, divide this by temperature, and that's all fine. And we get to this function down here. So mCp dt over T, dq equals dq over T plus V dP over T. Now, these things, this term and this term, look interesting, and we can take them, we can analyze them a bit further. We can move on. And in particular, we can use the ideal gas law. And let me just rewrite the equation here. So first of all, we move this term over here. And so we have dq over T equals minus dP over T, I hope I remember correctly, plus mCp dt over T. And that's fine. Remember the first law, remember the ideal gas law, PV equals mRT, okay? And so T, oh, sorry, there was a V that I forgot. So V over T, we can rewrite it in terms of mR and P. This from here, there follows that V over T, pardon me for squeezing everything in a corner up there, but V over T, you can do it better than me, mR over P. Okay, and so this is minus mR dP over P plus mCp dt over T. Okay, fantastic. So now what we can do is to notice that these are essentially differentials of logarithms, dx over x. What can I write this here? Dx over x is d log x. By log, I mean natural logarithm. Some people write ln. It's the same thing. I don't like ln for some reason. And so I just write d log. I hope that's clear. Yeah, so I wrote dln here. I hope I'm not confusing everybody. Ln and log, I mean the same thing, just natural logarithm, okay? So this is equals to minus m r d log p plus m cp d log t. Now, this we can always rewrite the R. We can take M and CP out, and this becomes minus R over CP, logarithm of P. Interesting that R over CP is popping up again. Plus, sorry, I forgot a D. D log T. Okay. However, you know the laws of logarithms, and so everything that's in front of the logarithm can be taken to the power of the argument of the logarithm. And so this becomes MCP d log of 1 over P to the R over CP plus d log T. Sum of two logarithms is the product of their arguments, is the logarithm of the product of their arguments. And so you put everything together. These are constants, and so they can always go inside of the exact differential. You put everything together, and you get to this. Okay? So what do we have here, and why is this interesting? Well, now we started with these very small changes, and we started with these very small changes. We put everything together, and we got some quantity here in the left-hand side that was equal to an exact differential. Now, what does that mean? Well, if you have an equality, A equals B, and B is an exact differential, what is A going to be? Well, it's going to be an exact differential, right? Because that's what an equality is, you know? And so we got to the result that dq over t is an exact differential. If it's an exact differential, it means that when you take an integral, it doesn't matter the path that you're taking, okay? Now, this quantity, dq over t, is called entropy, or is how we define entropy, okay? There are many ways, by the way, there are many ways to write down the entropy function, because Q, the heat, can be many things, many different things. We saw it last time when we talked about ideal gases and the first principle. We saw that there were many ways to write Q in isothermal processes and isochoric processes and isobaric processes, yada, yada, yada. And so because there are all these different ways to write down Q, there are many different ways to write down F. But the important thing is that now this quantity here is one way to write down entropy. Okay. Excellent. Okay, so in case you had never seen it, this is what entropy is. And in case you are familiar, I hope this is a good refresher. This is also interesting, and we don't need to spend too much time on this, but you can show that for a dry parcel, so for a parcel that doesn't have water vapor in it, the change in entropy during any kind of process is related to the change in potential temperature of the parcel. Okay? So you're going from A to B, for example, and A and B are two states of the gas, and you're going through a nice reversible path, whatever. You're asking, hey, how much does entropy change as you go from A to B? Well, the answer is very simple. Just compute the logarithm of the ratio between the potential temperature at the end over the potential temperature at the beginning of the parcel, and there's your answer. And this should also tell you why we care about entropy so much, or why we're talking about entropy, given that probably if you ever read papers, if you've ever been to talks, or if you talk to meteorologists, people don't really talk about entropy all that much, if we're being completely honest. But entropy is a close cousin to many variables that people use. So, for example, if theta A is some kind of constant that we don't really care about, then this you could use to say that, well, delta S is simply equal to mCp logarithm of theta plus some constant that, again, we don't really care about, okay? And so now you see changes in entropy and potential temperature are really, really closely related. Notice that I specified dry parcel over here. The reason why I did that is that water vapor, apart from making our life wonderful because it creates, it's a big greenhouse gas, because it makes clouds, and because it just makes life a lot easier because it rains and it makes life bearable. Water vapor complicates things a whole lot. And when you have water vapor, then you have to take into account changes due to the behavior of water vapor, okay? And so what you end up is that instead of talking about theta, the potential temperature, and we'll talk about this next time, if I'm not mistaken. I apologize if my writings is not particularly understandable. I hope it's clear what I'm writing. So instead of talking about potential temperature, we talk about a new kind of variable that we denote with theta E, that is usually called equivalent. I've written equilibrium too many times in my life, and so my hands just go in default mode. Excuse me. Equivalent. I was about to say equilibrium again. Equivalent potential temperature. Okay. Excellent. Another thing that I wanted to say is that sometimes when I talk about this quantity over here, this is called, just because you like my writing so much, let me write this down. Specific heat capacity. Voila. Now, sometimes I do use the word specific, and what I mean by that is, if you pardon my pun, is something very specific. In thermodynamics, when you use the word specific, typically you're referring to something that's divided by the mass of the gas that you're considering. And so if you take ds, d capital S, and you divide it by m, you get ds, the lowercase s, and this is called specific entropy. I'm not going to write this down because you'll hate me forever if I do. That is called specific entropy. Why do we like specific things instead of just things? Wasn't entropy enough? Well, entropy was kind of enough, but at the same time, maybe sometimes in life you don't know how much gas you have, or maybe you're dealing with a system that isn't really a gas in a cylinder, where it's easy to measure how much gas you have. Maybe you're thinking about the mixing between a cloudy parcel and the entire atmosphere, and good luck defining M at that point. So maybe sometimes in life it's more convenient to talk about, it's kind of like a density almost. if you will. Or, so quantities where the amount of gas that you're dealing with has been taken out, okay? And so that's why we define specific entropy, and specific entropy is so clearly, it's just one constant factor, but then it's essentially the logarithm of potential temperature. How nice is that? Okay, now we're ready to the second law of thermodynamics. Second law or principle, it's the same thing, really. There are many ways to define the second principle of thermodynamics. I like the word principle a little bit more, but again, law and principle, it's exactly the same thing. There are many ways to define what the second principle of thermodynamics is, and we'll see another one later on today. But essentially, the second principle, let me read it for you, says that there exists a function of parameters of the system. Notice I wrote extensive. We're going to talk about that in a minute. That function is a function of state, and changes from one state to another can be computed in this way, and such that the changes are always non-negative for an isolated system. Okay, let's unpack a few things. Okay. First of all, what does extensive mean? Well, hold on. We're going to talk about that in the next slide, I believe. So why is there a rev here? First of all. Well, because of the way we defined it, this function is well defined only if we're considering changes, only if we're considering reversible changes. But wait a minute, maybe sometimes I have some irreversible change in my system. So how about that? Well, in that case, no worry, because even if you're dealing with an irreversible change, you can still think about a reversible path that will lead you to that particular change, right? So, if you're going from A to B, and you're going, this is A, this is B, and you're going with some bizarre irreversible change, well, you can always engineer some reversible change that will lead you from A to B, such that you can always compute the entropy at A, you can always compute the entropy at B. As we said, entropy doesn't care how you go from A to B. As long as you're in A and as long as you're in B, that's what it is. The changes in entropy will be regardless of how you got there, okay? And so the fact that there's a reversible here, it means that when you think about entropy, you should think about changes that are reversible, okay? Also, why did I specify isolated system? Well, for non-isolated systems, there is a very simple way to show that the entropy actually decreases. If you think about something like a fridge, okay? If you were inside a fridge, what does the fridge do? What does the fridge do? The fridge extracts heat from cold objects and make them even colder, or extracts heat from objects and make them even colder. Now, one of the consequences of the second principle of thermodynamics, which we will not go too deep into, is that heat always flows from hot to cold objects or gases in general. So if you were to look at a fridge, you might think, oh, gee, second principle is violated because entropy is decreasing actually for the eggs that you have in your fridge. Well, yeah, sure. If you're considering your fridge, yeah, sure, absolutely. In your fridge, delta S fridge, so much fun when I make mistakes. Fridge, okay. This is less than 0. However, is your fridge an isolated system? Absolutely not. Your fridge, inside of your kitchen, your fridge is here, and it has a fan that takes heat out from the inside and blows the heat inside of your kitchen or somewhere else. I'm simplifying, but you get the idea. And this heat will then heat up the room. And if you were to compute ds room, that would be typically bigger than 0. And if you were to compute ds fridge plus ds room, well, there you go. It would still be, I can guarantee you, it would still be non-negative, okay? Okay, excellent. Now, let's talk about intensive and extensive quantities. Well, it's a lot of words, but it just means a very simple thing. Intensive quantities are quantities whose value does not depend on the amount of substance that you're considering. The density, for example, temperature, all things specific are intensive quantities, okay? So an example, temperature, for example. If you have, what could we say? Well, let's say boiling water. Boiling water is at 100 Celsius degrees, more or less. If you have a liter of boiling water, that's at 100 Celsius degrees. If you have 1,000 liters of boiling water, well, 1,000 degrees, 100 degrees. And so the temperature does not depend on how much of the substance you have. Extensive quantities are quantities whose value depend on the size of the system. An obvious choice is the volume. The volume is certainly dependent on how much you have. The volume of a box, of a big box, is bigger than a volume of a smaller box. I think that's kind of intuitive and common sense. So these are extensive quantities. Entropy is one example. Okay, specific entropy is an example of an intensive quantity. So that's what that's sort of the difference in why we're introducing specific things. Okay, the amount of a substance is proportional to the amount of a substance. I think we don't need to explain this. Okay. Now, you remember the last time that we talked about the first principle of thermodynamics and what the first principle of thermodynamics look like when you have certain specific situations. Okay. Well, the second principle of thermodynamics also has some special forms when we have special transformations. So if you have an isothermal transformation, okay, let's start from the first case. In isothermal transformations, internal energy, I hope this is clear by now, remains unchanged. And so total changes in heat content equals the total work that is done, not changes in work, the work that is done. And therefore, delta S, the change in entropy, is not smaller than the ratio between work and temperature. In adiabatic transformations, delta Q is 0. By definition, no heat is exchanged between the system and the environment, and so changes in entropy are 0 or bigger than 0. In isentropic transformations, so usually we have delta S, okay? For isentropic transformations, this is 0, and so delta Q is typically less than 0, okay? And then you can show that in isochoric transformations, isochoric means that the volume remains unchanged. Then delta S is not smaller than the logarithm of the ratios of the temperature, the final and initial temperature. And same thing is true for isobaric transformations, except that the factor in front changes. So here is the heat capacity at constant volume. This is entropy, so this is the heat capacity. If this was specific entropy, this would be specific heat capacity. Just keep that in mind. And for isobaric transformation, this is the heat capacity at constant pressure. Okay, so this is just simple cases where the writings it's easier to write down. It's easier to write down the form of your entropy. Okay. Now, we will not go through the derivation of these formula because I don't want to be too, I don't want to be too cruel and to spend a lot of time on deriving things. But there are simple ways to write and to rewrite the entropy for an ideal gas. And in particular for an ideal gas that is completely dry. So an ideal gas that doesn't have water vapor. Okay. And let's see. Okay. So we saw a few slides before that this was how we defined S in terms of logarithm of the potential temperature. Remember that potential temperature theta equals T times P over P0 R Cp. Okay, so if you have two different thetas, you can take the ratio between these two, and this is what you end up with. This is a bit an unhappy notation. Usually we write it as P0, but because I'm using a 0 here, it could actually confuse it. Let's say P prime. Okay, so theta over theta 0 will be T over T0 times the P prime simplifies between the two. So this would be P. Actually, my apologies, because the prime is the numerator. Sorry. Okay. I should have written it with a minus otherwise. So this would be P0 over P R over Cp. Okay. If you flip this, this gets a minus, and that's exactly what we wrote here. Now, we can use two simple identities. The first one is ideal gas law, P equals mRT over V. And also, for generic ideal gas, monoatomic, diatomic, we don't know, U equals F over 2 mRT. I hope this you remember from last time. And now you can plug things in here. And what you end up is that entropy depends on internal energy and the volume. What is the advantage of having something like this? It's just that in this case, entropy is related to things that are extensive variables, whereas in here, temperature and pressure, we said that these were intensive quantities. So this should also clarify that the fact that something is an extensive variable doesn't mean that it cannot be written that it's only a function of extensive variables. M certainly is an extensive variable, but these guys are intensive variables, and there's no problem. Okay, as long as there's something extensive, then there's no problem. Here we just have the advantage that everything here is an extensive variable. Okay. Now, what's more, you can rearrange the last equation, and you can write internal energy as a function of entropy. Okay. Now, you might ask, why are we doing all this? Well, look, the only reason why we're doing all this is that at the end, we end up with these two relationships, okay? The partial derivative of U with respect to S, if you hold V and M constant, this you can show using, simple mathematical analysis and using some and using some thermodynamics law, you can show that this partial derivative equals temperature. The partial derivative of internal energy with respect to the volume of the system holding the mass and the entropy of the volume of the gas constant is equal to minus pressure. Okay, and this is interesting because now it's telling us something important about how internal energy changes with respect to volume and with respect to entropy. And it's telling us that essentially changes in a very simple way, which is, simple numbers here. And it's telling us that if we hold volume and mass constant, internal energy is directly proportional to entropy. Okay, T is always going to be constant, isn't it? And so if you increase entropy, internal energy is always going to increase. First interesting information. P is always going to be positive, and so this is always going to be negative. So if you're holding entropy and mass constant, but if you increase the volume, the internal energy of your gas is always going to go down. Okay, these thermodynamics relations are important not just because they tell you something about the gas and about how the properties of the gas change by varying some of the variables of the gas, but also because they may be useful one day when you're doing some math for whatever reason. So let's say that someone asks you, hey, suppose that I give you U as a function of S, V, and M, and I ask you, what's the differential? Can you write down the differential of U, small changes in U without, knowing much else, but these guys over here. And so this, by definition, the differential is going to be partial U, partial S, holding V and M constant, times ds, plus partial U, partial V, dV, holding S and M constant, plus du over dm. Now, notice that so far we're never talking about changes in the mass of the gas. And that's just because things get really complicated when you talk about changes in mass. So let's assume that dm equals to 0, okay? And you're left with these two things. These could be anything, and, God knows what they are. But because you computed this very simple relationship, well, without knowing much else, you can very simply write this as T ds minus P dV. Okay? Which is interesting. It's an interesting way to write this down. Should this be a surprising form? Well, maybe not. Or, is this consistent with what we've talked about so far? Well, maybe not. If you allow me to take a little detour, let's take this on the other side. T ds equals du plus dv, P dv. Now, allow me to divide everything by T. But what was the first principle of thermodynamics? So it all makes sense in the end. We could have gotten there in some other way. But things aren't always that easy, so be grateful for these kinds of relationships when you're dealing with stuff, when you're deriving stuff. Okay, the next thing I wanted to talk to you about is something that will not be entirely relevant for the rest of the class, but those of you who study hurricanes and like hurricanes may encounter this at some point. And what I'm talking about is the Carnot cycle, named after some French guy who thought about it or discovered it first. The Carnot cycle consists of a simple closed loop process that is made of two isothermal transformations. and two adiabatic transformations. So in a PV diagram, which we kind of like, we start from point number 1, and we have an isothermal transformation. Okay, this is an isotherm at temperature T1. Does it make sense that an isotherm would look like this, I ask you? Well, let's think about it. PV equals an MRT. Okay? Let's hold M and R constant. Okay? And let's say we want to keep this value fixed at T1, which is this one. And so P, which is the dependent variable here, is MRT1, which is some kind of constant, divided by V, which is the independent variable. And so as you're decreasing the volume, P increases and vice versa. So it kind of makes sense that T has this curve. Okay, just saying. Okay, so we have an isothermal transformation and in particular an isothermal expansion. Okay. Then we have, this is accompanied by an adiabatic expansion. And does it make sense that it looks like this? Well, in adiabatic transformations, we know that PV gamma is constant. So we do expect the system to move on a curve that is different from this one that we derived, for the PV equals constant, because gamma is a number that's greater than 1, and so we expect this to be different. So we have this expansion. Then we have an isothermal expansion, and then we have an isothermal compression, and then we have an adiabatic compression. In these two segments, 1, 2, and then 3 and 4, heat is exchanged. Okay. Now we can do all the derivations. Excuse me. Okay. Okay. In terms of work and internal energy, let's think about this for a moment. So here we're doing an adiabatic transformation. An isothermal transformation. So first thing that we learn is that internal energy remains unchanged. Okay. And so the work that is done going from volume at point 1 and volume at point 2. Here I used A, B, C, D, but it's exactly the same thing. I hope this is not too confusing. The changes in volume correspond to work that is done, and in this case, work equals to the heat that is exchanged. Excellent. And this can be simply computed as the ratio between these two volumes. Here, using 1 and 2, this would be mRT1 log of V2 over V1. Okay. Notice also this, I forgot to mention, but it's very important that T1 is greater than T2. Okay. So the expansion happens at a warmer temperature. And in this case, heat is absorbed by the system. Then we have an adiabatic transformation. Okay. In adiabatic transformation, heat is not exchanged. Okay. And changes in internal energy are simply related to the work that is done because heat is not exchanged. How to compute work is complicated because PV gamma is constant, and then you have to integrate that, and it's too complicated. But we know how to compute changes in internal energy because internal energy is just a function of temperature. And so that is simply given by the difference between the two temperatures, T1 minus T2 or TH minus TC, hot and cold. And then for the other two processes, it's exactly the same with a flip sign, okay? We can also compute changes in entropy, okay? And where is entropy going to change? Let's assume that these changes are very, very slow, quasi-steady, and reversible, where is entropy going to change on these different branches? Well, it's going to change where heat is exchanged, isn't it? And so it's going to change here, and it's going to change here. It's not going to change here because these are adiabatic processes. And by definition, the change in entropy here is given by QH over TH, and this is minus QC TC, meaning that it decreases, okay? This is a cyclic process, so we end up exactly where we started from, okay? And again, reversible process, we end up where we started from. Entropy is a function of state, and so the total change in entropy, so change in here, plus here, plus here, plus here, must be 0. These two are 0, so some of these two changes must be 0, okay? Or this equals minus this. And what this tells us, if you sum these two and put an equal sign, this tells us that QH over TH plus minus, remember there's a minus here, QC over TC equals 0, which leads us to this. Okay? So the ratio between the two temperatures is also the ratio between the heat that is exchanged. Which is also interesting, and you're probably starting to see where we're going with this. Even if the system, so this suggests that there's something strange with the heat that is exchanged, right? Because QH and QC cannot be equal now, can they? Because if they were, if the system in this cycle had absorbed as much heat as it had given out, then these two would have to be equal, TH and TC, but they're not. Let me move on. So QH is what is extracted from some kind of reservoir of heat. QC is given back. But precisely because of this relationship here, we have that QH equals QC times TH over TC, and we said that TH is bigger than TC, so this will be bigger than QC, okay? So more heat is extracted than is given back. And this is interesting because this is another way of seeing the second principle of thermodynamics. Now, I really want to put an emphasis on this, and I would invite everyone to really think about this for a moment, because this is a very, very deep statement. More heat is extracted than is given back. Another way to think about this is that, or an equivalent formulation of this, is that all the work can always be turned into heat, but not all the heat can be continuously turned into work. I don't know, let's just pause for a moment and let's just think about this. We saw in the first principle of thermodynamics, we talked about the internal energy. We talked about how the internal energy is related to heat and to work. But somehow there is something very profound in noticing that heat and work, although they look kind of similar in the way that they add up to the internal energy, changes in internal energy, they're actually not that similar. And that there's something about heat that cannot be given back. And that's another way to think about the second principle of thermodynamics. That heat somehow gets lost in ways that work isn't, and in ways that other things aren't. And another way to think about the second principle of thermodynamics is to define an efficiency, which is how much heat is lost forever over the heat that was taken. What's the percentage of the initial heat that is never given back? And this, because of this relationship up here, you can write it as 1 minus dc over th. And eta, this is always going to be, because these are both positive, this is always going to be less than 1. Eta you could think of as the performance of some machine that you've built. In this case, it's a Carnot cycle, but you could think of just a generic machine. How much heat is your machine taking compared to the heat that is given back? It could be some kind of battery, for example. Battery is different because it's turning chemistry into heat, but in a way, it's kind of the same thing. You're accumulating heat in the form of some kind of chemical energy, and then you allow it to flow back in some kind of system, and you're giving back heat. Well, the heat that you can give back is never going to be equal to the heat that was given to you. So you can never generate heat. You cannot give back all the heat that you've taken. You're always going to be able to give back something less of what you actually took. Doesn't matter what machine you build, doesn't matter how you build it, doesn't matter if it's mechanical, doesn't matter if it has, I don't know, weird stuff in it, if it's a complicated machine or if it's a simple machine. You're never, ever, ever going to be able to give back all the energy that you took. And that to me is a very profound statement. Okay, last thing, I just wanted to mention, we talked about enthalpy last time, and can we ever have enough of state functions? Well, I don't think so. And Gibbs energy is another great state function that is widely used and that we will use actually. And so it's good to introduce it. The way that we introduce these things is it always looks kind of ad hoc. That someone told me how to write these things down and somehow I knew them. There is a way to relate all these things to each other, but I don't want to get too much into it. But essentially, if you notice, when you have a state function, you always seem to be able to get another state function. Let's say that you have a state function f. You always seem to be able to get another state function g in this way, minus x times y, where x and y are some variables. If you notice how we introduced enthalpy, that was exactly how we did it. So, is there anything more to this way of deriving things? Well, yeah, there is, but we don't have time to get too deep into this. And so Gibbs energy is defined as enthalpy minus the product of temperature and entropy. And in a differential form, dg is vdp minus sdt. Okay. Gibbs energy is helpful because sometimes when you're dealing with chemical reactions, Gibbs energy is the one that can tell you where the chemical reaction is actually going. Are there other functions that we can define? Well, of course, there are other state functions that we can define. One that we will not spend too much time on, and actually I'll just mention it here, is the Helmholtz. Did I spell this right? Nope. Sorry, I always get German names wrong. Let me write it like this so everybody's happy. This is called the Helmholtz function. And how is it defined? Well, guess what? F is internal energy minus T times S. So again, it's a simple way, and it's a simple way to define these quantities. Just as an FYI, the fact that all these different quantities could be related to each other became obvious much later than Helmholtz and Gibbs' time. Like, it's not like it wasn't actually that simple back in the days to get new state functions. Just because it's simple now is just because we realized a lot of things, and we decided we could use a lot of math, and the math that we discovered or invented, depending on how you think about math, kind of helps us in the process. But back in the days, this machinery wasn't around, and so it wasn't that simple that people are just sitting around and saying, "Oh, actually, if you do this on internal energy, you get this new function. I'll just name it after me." So it wasn't actually that simple. Just as an FYI. Okay. Anyway, and final thing I wanted to say today is that there's two things that we want to keep in mind. First thing, we can also compute, we can again show, we will not do this, but you could show that there are two nice relationships that relate Gibbs energy to pressure, nice relationships that relate Gibbs energy with volume and entropy. And these relationships, by the way, these are usually called thermodynamic potentials, these kinds of relationships, D, H, D stuff, D, G, DT, and the ones that we saw, these kinds of relationship. These are called thermodynamic potentials in general. And finally, this is specific. Once you define the specific Gibbs energy, there's a simple way to write it in terms of simple variables of the ideal gas, and this is the simple way to write it down. So this is just this is the last thing that I wanted to say. I think this is pretty much all I had to say for today. Just checking. Yeah, this is pretty much all I had to say for today's class. As usual, if you have any question, please let me know. Anything related to this class, anything related to previous classes, if there was something that was not clear and that you'd like me to go over, please let me know, and I'll be more than happy to go over it with you. Otherwise, thank you so much for listening, and I'll see you for next class.